Okay, next up we're going to look at subatomic particles. There's actually over 100 different subatomic particles that have been identified, but as its name would suggest, what does subatomic mean? Right, within an atom. So they're basically smaller than an atom. So these are particles that are smaller than an atom. And the ones we are going to be familiar with or accountable for are protons, neutrons, and electrons. Good. Protons, neutrons, and electrons. And you need to know what the charge of each of these particles would be. Protons are positive, neutrons are neutral, and electrons are negative. You should know the symbols we use, which are very simple. It's the first letter of each word. P, N, and E. And sometimes we show it the P positive, N in the superscript is 0, and E with a negative charge. Then when it comes to their mass, let's look at the mass. On your conversion sheet, and you don't need to pull this out unless it's just handy right there, but on your conversion sheet, it shows the mass of each of these particles in SI units, which would be the kilogram. And you'll see that these masses in kilograms, are these really big masses or really little? Really little, exactly. But you're going to see that two of these masses are very close to each other, and they would be proton and neutron. And the electron, is this bigger or smaller?
Smaller.
All right, a little smaller. It's a lot smaller. And so, turns out that we use some more convenient units when we work with these masses, and we measure them in units called atomic mass units. And so, in AMUs, we need to know these masses in units of AMUs, which again, an AMU stands for atomic mass unit. If you wind up taking a biology class, you'll probably hear things measured in daltons, but a dalton is the same thing as an AMU. An approximate mass of a proton is about 1 AMU. A neutron is about 1 AMU. The squiggly line means about. And remember, an electron is much smaller in mass, so we say its mass is about 0 AMUs. When in reality, you don't need to memorize this particular value, but if you really wanted to know its exact value, it's a fraction of 1 over 1,857 AMUs. So it does have mass, it's just that its mass is very small. So we say then in comparison that its mass is about 0, and we wind up using these approximate mass values. So then what we do from here is we are going to assign some important useful information of these, and we are going to look at some values related to the periodic table. And I guess you need to get out your periodic table anyhow. So if you didn't get it out already, let's get it out. And if anybody needs a periodic table, I have some more that are handy. Anybody else need a fresh one? Anybody else? Any others? So now we're going to again assign some important information to the periodic table here. And the first thing we're going to look at is this number that's inside of each box at the very top. This number here is called the atomic number. And the number in the bottom of each box is called the atomic mass. Good, the atomic mass. The atomic mass is given in units of AMUs. Now we won't get to the atomic mass until probably about half an hour from now. But let's start with the atomic number. We say that the atomic number, which by the way we label with the letter Z, we say that the atomic number is equal to the number of protons in the nucleus of one atom of a given element. And then we could say it is also equal to the number of electrons, exactly. But the number of electrons comes with the qualifier, and that is if the atom is neutral. And so the correct definition is this one right here. That is, it is the number of neutrons in the nucleus of one atom of an element. So what I've circled is the definition. But it turns out that if the atom is electrically neutral, that it's also equal to the number of electrons. And for today, all of our atoms are going to be neutral. Starting Tuesday, then they're no longer going to be neutral. But today, they're neutral. Okay, so it's easy. Today, protons, electrons will be the same. Starting Tuesday, they'll be different. Okay, now another value that we're going to look at is called the mass number. And the mass number, and this is where it doesn't make sense to me, is designated by the letter A. Now why doesn't that make sense? Well, to me, it makes more sense that the A would stand for the atomic number, but it doesn't. And I didn't make this stuff up, okay? It's just what it is. But the mass number is designated by the letter A. And we say that the mass number is equal to the sum of the protons and neutrons in one atom of a particular isotope. So now if we compare these two definitions, an atomic number is just the number of protons, while the mass number is the number of protons and neutrons. And what's interesting about the mass number is this. We remember that the mass of a proton and neutron is about the same, which is about 1 AMU. So if we know the mass number, let's say that the mass number of an isotope is 18, what that means is that the mass of that isotope is about 18 AMUs. So the mass number is a number of protons and neutrons summed together, and it also represents its mass in approximate AMUs. But in giving this definition, we gave one more word that needs to be defined, and that is the word isotope. And we define an isotope like this. We define an isotope as being atoms of the same element that have a different number of neutrons. So if we're talking about the same element, that means they're all going to have the same number of protons. And that's what the word isotope means. The prefix iso means equal or same. Good. And so this is same protons. We have isotones, which would be same number of neutrons. But isotopes, the P there, tells us it's the same number of protons. With that in mind then, we might look at the periodic table and we'll say, well, how do we know about isotopes? In other words, if I'm looking at something like oxygen, how do I know how many isotopes there are of oxygen and what they are? If I look at fluorine, how do I know how many there are and what there are? And the answer to that question is you don't, with some exceptions. And there are about 20 elements where we do know the number of isotopes of those elements, at least in terms of whether or not they're naturally occurring. And I guess it's easiest to probably look at this periodic table up here. You look at atomic number 43, which is technetium, number 61, which is promethium, and what do you notice about these symbols compared to the rest of the periodic table? Yes, these are written in outline letters. And so number 43 is written in outline letters, number 61 in outline letters, and then everything from 93 on up is written in outline letters. Now there's something that goes on with the fonts on the college printers, and I have no idea what it is, but it makes some really funky characters when you try to print outline fonts. So your periodic table does not have outline fonts, but rather has them italicized. So if you look at number 43, you'll see its symbol is italicized. Number 61 is italicized, and 93 on up are italicized. And here's what you need to know about those that are italicized on there, or the ones that are in outline letters up here. And that is, those elements have 0 naturally occurring isotopes. When we say that there's 0 naturally occurring isotopes, what that means is we go and try to dig up a hole somewhere and analyze those elements, we aren't going to find those elements written in outline letters anywhere in the world. They won't be found. The only place that we know of these elements is they've been created by humans. They've been created in the laboratory. Now the other thing about them is that when we see a number in parentheses in here, the number in parentheses represents the most common isotope of that element. So for ones that have numbers in parentheses, these represent the most common isotope of that particular element. And so in the case of neptunium, for example, neptunium-237 is how we pronounce this, is the most commonly synthesized isotope of neptunium in the laboratory. Now I realize that there's some others that have parentheses on them as well, that do have naturally occurring isotopes, like you see polonium, astatine, radon, francium, radon, and so forth. Even though they are found in nature, they are not very common in nature, but these represent the mass numbers of the most common isotopes found in nature. So they still represent the most common isotopes. But the ones that are italicized are the ones that we have 0 naturally occurring isotopes. Now for the rest of them, we need to find some source that would give us that information. And that source is going to be a periodic table that I have linked into the content portion of your D2L course.